Good morning, good afternoon, and good evening, everyone. Welcome to the TFTC General Webinar Series. I hope you all enjoying the spring breeze and blossoms, as well as our cars becoming dirty, all because of pollens. Today, we have a great speaker, Eunhan, who will share his insight on the topic named A Physics-Informed Machine Learning for Generalized Bathtub Model in Large-Scale Urban Networks. And we're excited to have all of you here with us today. Eunhan is a PhD student in the Lyle School of Civil Engineering at Purdue University, and he is advised by Dr. Satish Ukusuri since August 2020. His research interests are traffic dynamics modeling in large-scale urban areas from physics-informed machine learning and cyber-physical systems of traffic road networks under connected and autonomous vehicles environment. Previously, he completed his bachelor's and master's in civil and environmental engineering at Seoul National University. Now, please join me in welcoming Eunhan to the webinar. Now the floor is yours, Eunhan.
Yes, thank you. Hello, everyone. Thank you, Garion, and all committee members, the ACP50, for giving me an opportunity to present my research work. My topic is a physics-informed machine learning for generalized bathtub model in large-scale urban networks. I co-work with Dr. Satish Ukusuri, Dr. Ludovic Leclerc, and PhD candidate Jia Wei at Purdue. I'm Eunhan. I'm a third-year PhD student in the Department of Civil Engineering at Purdue. I will start my presentation. Can you see my screen?
Yes.
Okay. Thank you. I'd like to briefly explain network traffic dynamics. First, network traffic dynamics are formulated based on a macroscopic fundamental diagram. Many of you know this one, so I will briefly explain this one. The MFD was discovered by Gerolaminis and Daganzo in 2008. MFD explains the network level relationships among traffic flow variables like traffic flow rate Q, traffic density K, and speed V. Sorry. So in the figure on the right side, you can see the MFD showing the relationship between traffic flow and traffic density. So this plot is estimated through field observations like loop detectors data. We can find the average speed through MFD. So average speed is function of NT, and the number of vehicles can be found by dividing the traffic density by the length of that link. And then network traffic dynamics models change in traffic state over time based on MFD. The basic concept of network traffic dynamics is that the change in the number of vehicles is calculated as the difference between the inflow rate and the outflow rate. So FT is inflow rate and outflow is GT. If you think about it, it is similar to the phenomena of the putting water in a bathtub. So when you turn on the water in your bathtub, you can easily find that the water fills up over time, right? So in this way, by considering the city network as a reservoir, we can estimate the number of vehicles in the city network by accumulating the difference between the inflow flow rate and the outflow rate. It is the basic concept of network traffic dynamics. Okay, so there are 4 crucial network traffic dynamics models. First one is the bathtub model. Bathtub model was developed by Professor Vickery in 1991, and then Professor Daganzo proposed accumulation-based model. And then there are some limitations. I will briefly these limitations later. And then for overcoming these limitations of accumulation-based model, in 2017, a tree-based model was developed. And then generalized bathtub model was proposed by the Professor Wen Longjian. in 2020. So I briefly explain what are differences among these type of models. I want to compare network traffic dynamics crucial models. First, accumulation-based model was developed by Generalized and Professor Daganzo in 2007 and 8. This model assumes that trip length is constant for all vehicles as L. Its governing equations are ordinary differential equations with respect to time t, and then its advantage is very simple, and then it can be easily implemented in any load networks. However, its limitations is poor accuracy in sudden demand changes. It derives from the strong assumption the trip length is constant for all vehicle as L. For overcoming these limitations, in 2017, a trip-based model was developed. So this model assumes that trip length has its own trip length, Li. I is the vehicle index. Each equations are similar with accumulation-based model. Its advantages are, first one is the tracking of each vehicle, and then it can consider each own trip length, Li. However, this model have two limitations. First, high computation effort, and then second one, it cannot handle with uncertainty of real-world data. So, and then there are another approaches about the Bathtub model. So this model was proposed by Professor Vickery in 1991, and then its paper was published in 2020. This traditional Bathtub model is similar to accumulation-based model. It assumes that trip length has its own trip length, and then trip length distribution follows a negative exponential distribution. This is a very strong assumption, and then some previous studies show that in real world, trip length distributions doesn't follow any the negative exponential distributions. So it makes some limitations that is similar to accumulation-based model. It is poor accuracy by NED assumption. NED assumption is also very strong assumptions for overcoming this limitation. In 2020, Professor Wenlongjin developed generalized Bathtub model. This model relaxes the strong assumptions, NED assumptions. So in this model, trip length has its own trip length for any arbitrary distributions. And then he adopted a new dimension that is x. X is remaining distance. So these three types model has just one dimension, time t. However, in generalized Bathtub model GBM, it has two dimensions space x and t. X is the remaining distance and t is the time instance. Its advantages are tracking of each vehicles, and then it can model trips with remaining distance x. However, it has also some limitations similar to a trip-based model. So I hope to emphasize two main the limitations. First, there are few implementations in real-world networks, and then they can provide discretized solutions by its proposed solutions algorithms. So I introduced physics-informed machine learning to overcome these limitations from previous studies. PIM models integrate machine learning and physics models for taking advantage of them. Many previous studies called these consideration of the physics models as physics regularization. This is a concept of PIM models. As you can see this figure, x is input, x is the coordinates of the Galvani equations as input. I will be explaining later in our study. In our study, x is remaining distance and time t, time instance t are used as inputs in our models. And then theta is a set of weights in hidden layers of multi-layer neural network. From these weights, we can calculate values of target variables such as traffic density. In our case, KTX. KTX will be explained later. So here is one question. So how do we learn or optimize these neural network models? Here, the physics models is used to calculate the loss required for neural network model learning. So I will explain details later. So PIM model can compute derivatives of its Galvani equations. So this is a very strong advantages for PIM approaches. So what I want to emphasize here is that the PIM model can increase the accuracy of the model by calculating the loss through the Galvani equations of the physics models. So there are three main challenges. First, strong assumptions of physics models like Bathtub model or accumulation-based model. So question is, how do we relax strong assumptions? So I will use machine learning models. However, if we use machine learning models, many machine learning models, they don't have any the physical relationship between traffic variables in the training process. So I will use PIML models. And then third one is limited applicability of network traffic dynamical models. So many previous models was tested on 6-force or other hypothetical settings. For overcoming these challenges, I used mobile location-based data in Indianapolis, and I doesn't use any strong assumption like any trim length distributions or other things. So I will bridge the gap between network traffic dynamics models and machine learning models. So the objective of this work is to propose a PIM model to describe the traffic dynamics for large-scale urban road networks with generalized bathtub model. So I will call it PIML GBM. Comparing to the physical traditional models, PIM GBM can effectively capture uncertainties of real data than previous work. And second one is PIM GBM can remove the efforts in model calibrations like speed, MFD relationship, or other things. And the last one is PIM GBM can estimate continuous traffic variables. In our study, KTX, not discrete variables. So I mentioned that GBM was proposed by Wenonjin. He proposed a discretized solution algorithms. That means that previous work can provide discrete solutions of KTX. But in our case, we can estimate continuous traffic variables values. Compared to machine learning models, PIM GBM is more robust with randomness from real data. And then we can outperform previous work from the physics regularization. Let's move on to the next part. It is preliminaries. I will briefly introduce 5 types of variables. First, network variables. Second one is inflow. Third one is outflow. Fourth, traffic state variables, and then the last one is active trip variables. So there are so many variables, right? So I hope to emphasize just KTX, this variable. This variable is main state variables like traffic density. This is very similar to traffic density variables. So the objective of GBM and my model is to estimate this variable from the Galvani equations like conservation laws. Since it can be difficult to intuitively understand KTX, what is KTX? So I'd like to explain in more details. What does it mean if x is zero? When x is zero, it means that the remaining distance is greater than zero, right? So it means or activities or traveling vehicles, right? So that is KT0 means traffic density KT. So what happens to KTX as x growth increases? As x increases, the remaining distance increases, right? So it means that KTX values decreases as x increases. So like this one. So I hope to emphasize this variable because this variable is main target variable in my model and generalized Bathtub model. So KTX is similar to traffic density. I'd like to introduce on GBM model proposed by Eunhan. I briefly explain this one. There are three conservation laws. First one is conservation of 3 miles. In this equation, first term is initial entering 3 miles, and second one is added 3 miles until time t, and third term is process 3 miles until time t. The sum of these terms is equivalent to remaining 3 miles. This is the conservations of 3 miles. Second law is conservation of total trips. Actually, these two types conservation laws also used in the other accumulation-based model and the Bathtub model. First term is cumulative outflow is equal to initial entering vehicles plus cumulative inflow minus number of active vehicles. So this is a second conservation law. I have to emphasize on this third law because this third law describe the evolution of KTX, the main variable of GBM. So I will use this third law in my PIM model training process by physics regularization. So I will explain this one in my training process. So now that we've covered the preliminaries about the GBM model, so let's take a look at methodology. First, problem statement. Calculating the derivatives of Galvani equations like three conservation laws or third conservation laws of GBM is challenging. So previous studies proposed discretized solution algorithms for solving differential equations. In my model, PIM GBM model is defined in the space-time domain, where space x means remaining distance and time t is time instance. And then we assume that all active vehicles or all traveling vehicles have the same speed at time t, and the distribution for any inflow to remaining distance to the pi tx. It is given empirical distribution. It does not require any calibration related to the speed MFT relationship. The figure on the right side, it represents the space-time domain. So x is the time, x-axis is time t, and y-axis is remaining distance x. The PIM GBM model calculates derivatives at any point in this space with a neural network through physics regularization. That is, the PIM GBM model tries to overcome the limitations of previous models by providing just discretized solution. So like this one. So I hope to calculate these derivatives from the physics regularizations and auto differentiations from the TensorFlow the libraries. So this figure is a PIM GBM framework. PIM GBM model use observations, auxiliary points, ground truths, and trip informations. All of them are obtained through actual data, real data. We use mobile location data. But these auxiliary points, it is virtual data. So these auxiliary points are not obtained from the real world data. We can set the number of auxiliary points. I will explain this later. In PIM GBM model, it includes a multi-layer neural network and auto differentiation and then loss function. Finally, we can get the learned network parameter. We denote double star, from which we can estimate the continuous value of KTX. So our the final output is KTX estimations. So we denoted the K hat TX. I'd like to explain input data. So unlike other neural networks, the PIM model has a big difference in input data. That is the auxiliary point. So there are two inputs. First, observed points and auxiliary points. Observed points are denoted by O. Observed points are obtained from the mobile location-based data for training process. As you mentioned, auxiliary points are input randomly selected by the researcher. So it is just a hypothetical point for learning physics knowledge and calculating derivatives of PDE. The more auxiliary points are used, like here are just the less auxiliary points, and then in this here, there are so many auxiliary points. So the more auxiliary points are used, the more regularization through physics knowledge, like third conservation law, can be promoted. So in other words, learning physics knowledge is proportional to the number of auxiliary points. So we can set the number of auxiliary points by ourselves for training process. I'd like to describe the PIM GBM architecture. So it consists of three main parts. First, multi-layer neural network and auto differentiation. And the third one is loss function. First, the multi-layer neural network takes time and space coordinates TX as input, and it can estimate KTF through the activation function hyperbolic tangent and weight in hidden layer. So we can get our final output in this neural network. It is estimated KTX. And then auto differentiation. This is the contribution of PIML GBM or PIML approaches. So this is for calculating derivatives for each the coordinates t and x. So it takes auxiliary point, time and space. So TA and XA. So how to and then we calculate these derivatives from the TensorFlow function TF gradient tape. So by using this one, we can get some values and derivatives of this one. So this one, these are used in calculating the residue of the third conservation law of GBM. So I will explain that on next slide. So many neural network use loss functions for training process and optimize their own parameters. There are two types of loss functions. So first one is data loss, and then second one is a physics loss. many neural network use data loss, right? So target variable minus the estimated variable or predictions of the target variables. So it can be used many cases. However, physics loss, this make some differences between the PIM approaches and other neural networks. So physics loss is defined by residuals of third conservation equations from the auxiliary points. So data loss is calculated from observations, TO and SO. It is observed points. And then physics loss can be calculated from the auxiliary points, so TA and XA. So for training our PIM GBM model, we can use total loss. It is a weighted sum between data loss and physics loss. This is training algorithm. So as you can see here, there are input, and then we use the LBFGS optimizer. This is proven from previous studies. Its performance is outperforming other optimizer like ADAM or other things. So I use LBFGS optimizer, and then before training process, we initialize some parameters and threshold. So termination criterion is first one is total loss is less than the predefined threshold, and then second one is the number of iterations reach the maximum number of iterations. So either these two types of criterion is satisfied, we terminate the training process. I will briefly describe the experimental settings. So for showing our performance of PIML GBM model, we test it on the Indianapolis road networks. So study area is Indianapolis, Marion County. The total length of road links is 4,851 miles. And then we analyze just 1 day to 24 hours. Temporal resolution is 15 minutes. And then remaining distance X resolution is 1 mile. So we can get data from mobile phone location data like 0, 1, 2, and then 75 miles. And then we can also estimate speed MFD relationship like this one from real world data. So as you can see, this plot is average speed. This one is inflow trim rate. And then this one is speed MFD relationships from mobile location data. I compare two benchmark models. So first one is a GBM models. It was proposed by Wenlong Jin in 2020. It is a discrete time solution algorithm. The objective of comparing with this one is to verify the outstanding performance of PIM GBM to capturing uncertainties. And then second benchmark model is pure multi-layer neural network. So it has same architecture with PIM GBM model, except for the physics loss. That means that total loss just is equivalent to the data loss. So there is no any physics loss. You can quantify the impact of adding the physics knowledge in the training process or the physics regularization. So as you can see, this algorithm was proposed by Wenlong Jin. So I cited this algorithm from the Wenlong Jin's papers. And then I hope to validate my the implementations with Wenlong Jin's research. So this is a Wenlong Jin's research in the paper. I implement these steps and remaining steps in my coding. So as you can see, this is a very similar one, and then this graph is also similar. So blue one, in this case, red one is equivalent to my the plot in the line. Yeah. So based on this benchmark model one and pure neural network, I calculate evaluation metrics, MAE, RMSE, and relative L2 errors. So let's look at this table. We can see that PIM and GBM outperforms other models, right? So in more details, by comparing GBM and PIM and GBM model, you can verify the outstanding performance of PIM and GBM to capture uncertainties from real data, right? And then comparing PMNN, this is a pure multi-neural network without any physics loss, and a PIM and GBM model, we can quantify the impact of physics regularizations in the training process. I will show my results. So this plot is ground truth, and then each row in this figure shows the results of benchmark 1 GBM. This is benchmark 2 PMNN, and third row is PIM and GBM result. We represent log values to regularize the scale of the data, and then this is ground truth actual the KTX values. The second column is a plot representing KTX estimated by each the benchmark model and my model. And third column is the difference between the ground truth and the estimations. And fourth column is the absolute value of the difference between ground truth, this one, and then its estimation from each model. Let's look at the third columns. In the third column, red color means underestimation, and blue color means overestimations. In the case of PMNN, this one, this plot, it can be seen that internal points, excluding any boundary points like this one, this rectangular, this square, except for this one, the internal points cannot be estimated well, right? So this means that it is difficult to learn the evolution of KTX without any physics knowledge from conservation laws or other models, the Galvani equations. So it can be confirmed that PIM and GBM has less degree of underestimation or overestimation compared to other models, right? So the clarity is less than others. So, and then also evaluation metrics like this one support our result, our PIM and GBM model can outperform any other benchmark models result, right? So let's conclude. So our study proposed a PIM model to estimate the traffic states or demonstrate traffic dynamics in large urban areas from mobile location data. I hope to clarify our four main contributions. First one is estimating and predicting the number of trips. That means the KTX by using a deep neural network and boundary points without any theoretical assumptions like MFD calibration or other things. And second contribution is to quantify the ability of PIM and GBM to capture the uncertainty of traffic dynamics more accurately from the neural network structure by comparing existing benchmarks models. So first one is GBM, and second one is pure multi-layer neural network. Third one is to describe traffic dynamics over a continuous time distance domain with boundary points of by using our PIM and GBM model. So it is our strong contribution, I think. And the fourth one is to implement GBM to the real road network for describing traffic dynamics in large-scale urban area. Like in our case, it is Indianapolis road networks. So I used mobile phone location data for calculating tree characteristics and KTX values, and then we used the values for training process in our PIML GBM model. So these are cited references. Thank you for your attention. So I'd like to open the floor for questions. Thank you.
Thank you, Eunhan, for that insightful presentation. Personally, it was a really interesting topic that I wanted to listen about and hope everyone felt the same. You know, PIMLs are really hot method in many areas, not only the traffic flow. Now, I believe everyone can understand how the proposed model can overcome the interpretability problem of previous ML models and also has a good ability to estimate traffic states accurately. So thank you so much for your presentation again. Now the floor is open to the audience. If you have any questions for our speaker, please unmute yourself to cast a question.
Yeah, please let me know any questions about this one. Yeah.
Then
No one?
I would like to start a question.
Yeah.
At this moment, I see your main results plot is so interesting. I wonder this model showed a good performance around all density levels, like the performance as a function of density. Like maybe we could partition the result by the density level and see whether it is robust for all density levels.
So could you explain more details about your questions? So
yeah, many machine learning models have a good accuracy in aggregated level, but I think they don't really discover whether there is a tendency of accuracy by the density levels, although like they might turn out to be really vulnerable around critical density of the actual data. So I think this is physics informed, so it might overcome this limitation that they might not be they might be really accurate for aggregated level, but it might not be accurate for certain density levels.
Okay, so your question is about the PIML or other the neural network can outperform in just a aggregated level, right? So your question is about the performance in the just load link or certain areas. It is also outperformed from the PIM GBM model, right? So that is your question, right?
Yeah.
Okay. So actually, we test whole load networks, right? So in this case, there are actually it means that it assumes homogeneous the characteristic over or entire load networks, right? So the downtown, actually, it is similar to the suburban areas or other the areas. So it is our the limitations, and then we hope to extend on this type of model to the heterogeneous the PIM models over by clustering each the area with homogeneous characteristics like suburban areas or the downtown areas. So we can develop this performance from the just a whole node network into the several the cluster in load networks like the 5 zones or 9 zones in the Indianapolis. So it is the future directions of our research. Yeah.
I see. Thank you for your answers.
Yeah, thank you.
Yeah, Eunhan.
Hello.
Thanks for your presentation. This is COA from University of California, Irvine. Thanks for your work on the bathtub model. I'm wondering, the data that you calibrate bathtub model, what might be the penetration rate of the data? I spoke with Dr. Wenong Ji and asking questions how to calibrate the bathtub model. And he said if we have trajectory data and 100% market penetration rate, then you can calibrate. I'm wondering that there might be perfect case, but we know that it might not be perfect. Yeah, so I'm wondering, what's the penetration rate of data and how do you leverage them to?
Okay, so your question is about maybe mobile phone location data's penetration rate, right? It is correct?
Yeah, the penetration rate.
Yeah, so actually we get maybe 14 billion records in Indianapolis in 2019 March for 1 month. And then based on that data, first we use the data filtering, like the unusual data, like there is no any consistent with respect to location or time. We remove that, and then we estimate home. That is because we hope to how many the mobile phone users are measured in our data, right? So that is actually directly related to penetration rate, right? So we know the total population in this area. There are 1 million populations are there in the Indianapolis, and then we estimate the regular users. Regular users means that we assume there are the several days from the mobile phone location data, and then there are the specific area in the AM, like 7 a.m. to 10 a.m. It can be a record. We can estimate that is maybe home, right? So we can detect a home and regular users. So we get maybe about 7% of the penetration rate. So we calculate the multipliers of that penetration rate in our methodology. Yes.
So how does the data look like? It's also trajectory data, right?
Yeah, the trajectory data. Yeah.
Got it.
Yeah, so we can get the maybe 70,000 users in our mobile location data, right? So we can get a penetration like 70%. Yeah.
Yeah, thank you.
Did I answer your question?
Yeah.
Thank you.
Yeah, thank you.
Actually, I have some concepts about the calibrations about MFD relationship, right? So I use the benchmark model GBM Professor right? Professor Wenonji. So yeah, so actually for improving its performance, we should careful calibrations about that, right? So yeah, so I agree with your opinions, but in our result, we can show that the performance of our PIM GBM model, it can outperform the yes. So yeah, did I answer your question?
Yeah. Thank you.
Thank you for your question.
And I see there is a question coming from Shadi in the chat box who asks, thanks for the presentation. How do you determine parameter alpha in the total loss?
Okay. So actually, I briefly explain my result, and then actually I did a sensitivity analysis with various values of the alpha in total loss, like the alpha is equal to 0, 0.1, and to the 1.0. So I conduct sensitivity analysis with respect to alpha value, and then I select optimal alpha in PIM GBM model. So in this result, optimal alpha value is 1.4. So I execute several the implementations with respect to alpha value. Yes, I think I can answer your questions, Shadi. Yeah, thank you.
Great, thanks.
Yeah, so for the maintaining the presentation time period, so I briefly explain my results, but I did a sensitivity analysis with respect to the alpha value. It is a weight from between the data loss and physics loss, and then actually Shiwei, right? Shiwei's question is a very good point. So actually, I can answer your questions in my future published paper. Yeah, so there are more details about my calibrations and some other research.
Yeah. So we are currently also want to calibrate the bathtub model. But we don't have the trajectory data. So we are thinking of, but we have a DTA simulator.
Yeah.
We plan to use some data from that to calibrate.
Yeah. It's actually so. I reviewed the generalized bathtub model. Its limitations is about the data, right? So many of you know the loop detector data. So that means that we know any traffic flow rate or density and average speed from the loop detector. However, there is no any turbulence, right? So I think so mobile location data or other trajectory data can overcome these issues. And also I think right. It is very difficult. So I compared the ground truth with generalized bathtub models algorithm proposed by Jin, and then it also has good performance, but in our case, PIM GBM model can outperform it. Yeah,
sounds great. Is there any chance that we could access your research work?
Actually, this paper is in the review process. So if if I can get some good news, you can access these papers. Yeah,
sounds great. Best of luck. And a question about the uncertainty. How do you characterize uncertainty and how do you capture them in your work?
Yes. Actually,
accidents.
Accident. What?
Yeah. Do you characterize the accidents or some like weather, extreme weather as your uncertainty, and how do you capture them and how do you calibrate them in your form?
Actually, yes. So actually, we use the terminology of the uncertainties in our studies. That is, there are some noise in the real world networks, right? So we can get the average speed from the MFD relationship, right? So we can estimate exact value from them. However, in real world, there are so many noises, right? So we doesn't use any MFD relationship in our approaches from the deep learning neural network. Yeah, so that the reason why I use the terminology is uncertainties of real world data. That is, we can not any we cannot assume that any MFD relationship. We just use the data driven method. Yeah.
Yeah. Thank you so much.
Thank you.
Are there any more questions from audience?
Hello, this is Eunhan from Yonsei University in South Korea. And
hi.
Yeah, it was a very nice presentation. It was interesting, but I have one question in your page 20, table 2. The scale from the RMSE, it times 10 and minus 2. And I think that GBM, PMNN, and your proposed model has a very small difference, I think, because the real error is less than 1. They are all less than 1. So does it really have a very good contribution?
So clarify your questions about the research, right? So you're
Yeah.
saying that PIM and GBM models doesn't outperform than other works or ground truth. So could you clarify your questions?
I mean, your prediction accuracy performance shows better, but
Yep.
I don't think that's a big difference from the real scale. Because for GBM model, the RMSE is
okay.
0.47,
Yeah.
and it is still a good performance, I think. And does it really have a good performance?
Yeah, okay. So actually, your question is about the scale of these values, right? So as you can see, any this type of model like traffic state estimation or traffic state predictions, in this area, our performance just 1.1001. If value is also outperforms because I regularize these values between the minimum values from the maximum value. So it means that 0 means just 0, and then 1 means the maximum value in the ground truth data. So it means that if we can outperform just 0.1, that means that my model can outperform like 100 vehicles or 150 vehicles in the real world values. So this value is from the regularized target variables. So did I answer your questions? So actually that is from the scalability regularization.
Thank you.
Yeah. Did I answer your question?
Yes.
Right? Yeah.
Thank you.
Yeah.
All right. I think there is no more question from audience, and I think it's good time to end our webinar. Thank you again, Eunhan, for sharing your expertise today. Also, thank you to all of our participants for your engagements and thoughtful questions. If you would like to learn more about this topic, Eunhan will be happy to get in touch with you, I believe, right?
Yep.
And finally, we hope you will join us again for our next webinar. So you all have a great weekend and great spring break if you have one, and have a great rest of the day.
Yeah.